Okay. That is the previous one. Okay. Now we have this one, another example. The transfer function is 100 times 0.02 j omega plus 1 divided by j omega squared. Okay, so we know that the break is here at this 0 is 50. Yeah. The tau equals to 0.0 omega, and so it has when it is 50 radian per second, then it has the break. Now this one has 0, double pole at the origin. Yeah, double because of the square. Okay, from 100 first one, so the pole is at the origin. Okay, at the origin here, then square, since it is square, then at pole. So the decrease is at minus 40 decibel per decade. Okay, minus 40 decibel per decade. And the second one here, the pole, the break corner frequency is at 50 radian per second. Yeah, at this region. So 1 decade from that is 500 radian per second. And so before 50 here, then the magnitude or the asymptote is 0 decibel. After that, it increased by 20 decibel per decades. Okay. And the phase is from 0 until 90 degrees, yeah, with 45 degrees of asymptote, 45 degrees per decade increase. Okay, then one instant is drawn, then we can draw the composite, the combination of this between the 0 and 1 radian per second until 50 radian per second. So the it is just mainly because of this, yeah. So because the other combination is just 0. So this becomes minus 40 decibel per decades. Then after that, it is plus 20 decibel per decade. So the gradient decreases to minus 20 decibel per decades. Okay. The phase composite is the addition. So between 1 until 5 radian per second, it is minus 180 degrees. And then increases by 45 degrees per decade until 500 radian per second, then becomes asymptotic at minus 90 degree at this region. Okay, another example. J omega, the transfer characteristics is equal to 10 j omega divided by j omega plus 1 divided by j omega plus 10. So here we know that the break frequency is at 1 radian per second as well as 10 radian per second. But this one we need to convert into the standard form, so to become j omega tau plus 1. So this becomes 0.1 j omega plus 1 and divided by 10. So this becomes j omega. This is also divided by 10, becomes j omega. J omega divided by j omega plus 1 multiplied to j omega divided by 10 plus 1. Okay. Contribution from the first pole, the first zero is at 0. 0. So here then it increases by just 1, so 1 plus 20 decibel per decades. Yeah, at 1 radian per second, it is just 0 decibel. Increases then by 20 decibel per decades. The phase is plus 90 degree, yeah, because of the J. The J will introduce a 90 degree phase increase. Then the first 0 here, the first pole, j omega plus 1, so it has break frequency at 1 radian per second at this line. Okay, so before that the asymptote will be at 0 decibel. After that, then the asymptote, it will decrease by minus 20 decibel per decade. So here the phase is at the origin, it is 0 degree, then decrease by minus 45 degrees per decade, then until it reach minus 90 at frequency of 10 radian per second, then asymptotic at minus 90 degrees. The second pole is j omega divided by 10 plus 1. So here the break frequency is at 10 radian per second at this line. So before that, then the magnitude is asymptotic at 0 decibel at 0 decibel. After 10 radian per second, it will decrease by minus 20 decibel per decade. The phase, on the other hand, it starts from 0 degrees. Yeah, here 0 degrees, and then decreases by minus 45 degrees per decade until it reaches minus 90 degree at 100 radian per second. Okay. So each term is, we have drawn the magnitude characteristic and the phase characteristic, and we draw the composite. Okay, between 0.1 and 1, this is 0 decibel, and it has only this increasing component, 20 decibel per decades. After that, between 1 and 10 radian per second, this increasing and decreasing component cancel each other, so we only have flat component here. Okay. After that, this will cancel with this one, then we have only this decreasing component minus 30 decibel per decades. So this is the magnitude characteristic. The phase characteristic between 0.1 to 1, this is minus 90 degree, this is 0 degree. So we have decreasing minus 45 degree per decades here. So it will decrease from 90 degree until 45 degrees. Yeah. And after that, it decreases further here. And then after that, it is this is combined, yeah, with this is minus 90 degree per decades, while this one become minus 45 degrees per decades again. Now another example, a more complex function with complex conjugate pole. With complex conjugate pole, so we have here 25 j omega divided by j omega plus 0.5 j omega squared plus 4 j omega plus 100. So this is not yet in standard form. This we have to be expressed by dividing it with 0.5. This becomes j omega over 0.5 plus 1. So this is divided by 0.5 as well. So this becomes 0.25 divided by 0.5 divided by half is 50, but then we divide by 100 here to make it into 1. 50 divided by 100 equals to 0.5 j omega. So here, after dividing by 100, this becomes j omega divided by 10 squared. This becomes 4 divided by 100, so j omega divided by 25. Okay, so from the first 0 there, 0 at equals to 0, yeah, so here the magnitude here is 0 decibel at, this one is at 2, yeah, at 2 radian per second, 2 radian per second, then increasing by 20 decibel per decade. 20 decibel per decade. After that, the phase is always 90 degree because of the j here. Then we have j omega divided by 0.5 plus 1. The break frequency, the corner frequency is at 0.5. Yeah, so 0.5 means here. Okay. 0.5 radian per second. So before that, the asymptote is at 0 decibel. So we have to draw between 0.5 and 0.05 and 5 radian per second. Two regions. And here, so from there, this becomes 0 decibel before 0.5 radian per second. Then after that, decreases by minus 20 decibel per decade. Okay. The phase is before 0.05, the phase is at 0 degrees, then decreasing by minus 45 degree per decade until it reaches minus 90 at 5 radian per second. So until after that it becomes negative 90. Before that it is 0 degrees. After this one it becomes minus 90 degree phase. And the last one, so this is the quadratic form. The quadratic form. So below this one. So from here, then we derive first to zeta tau equals to 1 over 25. While the tau here equals to 0.5, and this is supposed to be j omega tau, 0.1. So from here, then the zeta equals to 0.2. Okay, zeta equals to 0.2. The tau equals 0.1. So here at 0.1 or at 10, at 10 radian per second here. This will be the corner frequency. Tau is 0.1, so the corner of break frequency is at 10 radian per second. And before that, so this is the breaking frequency. Okay. Before the phase angle is 0 degrees, after that, it's just negative 180 degrees, negative 180 degrees. Okay, so this is omega tau equals to 1. Then at this part, the magnitude will be minus 20 log 2 zeta. 2 times 0.2 equals to 0.4 log 0.4. So close to 8 decibel. So at this part, the magnitude is 8 decibel at radian at this breaking frequency. Omega tau equals 1 or omega equals to 10 radian per second. Okay, so this is the asymptote. Like this, so this cancel each other. This negative and positive become just flat. This become this is positive 20 decibel per decade. This is negative 20, negative 20 decibel per decade. But then remember that this has 8 decibel at omega equals to 10 radian per second. This increase. The phase similarly can be drawn from the composite. Behavior close to the corner of conjugate pole or zero is too dependent on damping ratio. This one. So that is why computer evaluation is better. So this is a practical approximation. So we don't use computer, we just try to approximate how will it look like, the magnitude characteristic and the phase characteristic. The better way is, of course, to use MATLAB or Python or Octave or any other computing software. So for example, here we have dj omega equals to 25 j omega divided by j omega plus 0.5 times, this is the quadratic term, j omega squared plus 4 of j omega plus 100. So first of all, we can use, this is not the standard form, but we can immediately put into the MATLAB software, or the numerator is for the first order is coefficient is 25, while for 0 coefficient it does not have any coefficient. So that's why you have to put 0, 25, 0. The denominator, it has, now since this is not in the polynomial, normal polynomial format, you have to use convolution function for polynomial multiplication. So convolution of 1, this is the first order coefficient, comma 0.5, the 0th order, and this one, comma 1 for the second order coefficient, plus 4, the first order coefficient, plus 100, the 0th order coefficient. So the denominator you obtain how many coefficient? 1, 2, 3, 4. So this, if you write down as polynomial, this becomes okay. So this becomes square 1 j omega cubic plus 4.5 j omega square plus 102 j omega plus 50. Okay, so this is in the, if you, you may check using your own manual multiplication. Then you can immediately draw the magnitude characteristic using this command, frequency numerator, comma denominator. And this is how it will look like. See here, this is during this, if we divide it by 100, so the radian is at, the tau will be at this one, 10 radian per second. So this is how it looks like. This is the phase as a function of the frequency. Yeah, if using computer, it is more straightforward. Another example. So this one is the previous example. This is the same example. So the same function. Yeah. Now you try to control the axis. The W, this is the log space. You draw from -1 until 3 to 100, defining the x-axis. Okay. Then the G is 25 times J times omega W. So the W here is the frequency domain. Okay. In a log space, logarithmic space, you're defining the x-axis at 200 points total from 10 to the power of -1 or 0.1 radian per second until 10 to the power of 3, 1000 radian per second, with 200 points total between them. And then we put the G equals to 25 times J times W divided by, why there is point here, so that it will multiply per element, divided by the denominator part, J omega plus 0.5 multiplied by J omega square plus 4J omega plus 100. This is the transfer function. Then subplot 2 into 1, this is to divide the figure into, using semi-log for the y-axis. So W, 20 times log 10 absolute of the G value. So this is the magnitude phase. Then grid, to put grid here, and the Y label will be in decibel. The Bode plot, the magnitude decimal. Repeating for phase, semi-log for the x-axis. Okay. W, unwrap to avoid jump from plus 180 degree to minus 180 degree. Then we put this angle and then draw the graph phase as a function of radian per second. Yeah. So here, if we compare with the previous one, this is smoother, yeah? Like this. While if we use our own equation, we try to put operation, it has this different response. Okay, let's do another example here. Gj omega equals to 0.5, 0.2 j omega plus 1 divided by j omega times square function, j omega divided by, this is already in standard form, j omega divided by 12, so this is the tau square, plus j omega divided by 36 plus 1. So the T2 here is this part, 1 plus 2 zeta j omega tau, this is j omega tau squared. So the tau is 1 over 12. Tau is 1 over 12. 2 zeta tau equals to 136. So then the zeta equals to 136 divided by 2 divided by tau. So equals to 1 over 6. Now let's approximate first manually. So the first term here, 0.2 divided by j omega, the pole is 0 pole, and at how many? 2, 0.2, the magnitude 0.2 until 2 radian per second. Between at 0.2, it is 0 decibel, and it decreases by minus 20 decibel per decade. Then the first 0, j omega plus 1. So the break frequency is at 1 radian per second. So here, before that, the asymptote will be 0 decibel. After that, it will increase by 20 decibel per decade. 20 decibel per decade. Okay, then this one, the quadratic expression. So tau, the break frequency is 1 over 12. Yeah? The omega will be 12 radian per second. 12 radian per second means somewhere here. This one, 12 radian per second. So before that, it is 0 decibel. After that, then it decreases by negative 40 decibel per decade. Okay, negative 40 decibel per decade until 120 radian per second. Now we have to find the response at the break frequency. Omega tau equals to 1, this one. So omega tau equal to 1 means omega equals to 12 radian per second here. Yeah, so equals to minus 20 log 2 zeta. 2 zeta is 2 over 6, 1/3, 20 minus 20 log negative minus 20 log 1/3, or equals to negative, so equals to 9.5 decibel. So this one, the magnitude is, there is a bit protruding, peak at 9.5 decibel. So then the composite between 0.1 until 1 is this one, decreasing at minus 20 decibel per decade from 10 until negative 1, negative 10, and 0, because this compensate each other. After that, it decreases by minus 40 decibel per decade. This is minus 40 decibel per decade. However, this is 0 decibel per decade, and this one at 12 radian per second, it has a value of 9.5 decibel. Okay, so actually then this one, the value will be something like this. Okay, 9.5 decibel. So this is if we draw using computer, using program. 0.20 omega. So see here, so if you compare with the previous one like this, and then there is an increase at the break frequency of 12 radian per second. Okay, and the phase, this is the phase frequency. We did not try to estimate the phase frequency. So here num 0.2, 1,1. Then the denominator is by convoluting this part. This is 1,0, and this one is 1/144. The coefficient of the second degree, j omega, and this is the coefficient is 136, 1/36. Then 1 as the zeroth coefficient. Then we just display it using this function. It's straightforward. Okay, if the previous examples show us how to estimate the graph, the Bode plot, from the corresponding transfer function. Now, can we estimate the transfer function, determining the transfer function from the Bode plot? So this is the inverse mechanism. So Bode plot is given, trying to estimate the transfer function. Inverse problem, determining the frequency characteristics. We will use only the composite asymptotes plot of the magnitude to postulate the transfer function. The slopes will provide them information of the order, whether it is 20 decibel per decade or minus 20 or 40 decibel per decade. If it is plus, then it is for the 0 for the numerator. If it is negative or decreasing, then we know that it is poles, the denominator. If it is negative 20 decibel per decade, then it is for a simple pole or simple 0. If it is for 40 decibel per decade, then it is quadratic expression. Okay, now we have this Bode plot from 0.01 radian per second until 0.1 radian per second. It is flat at 20 decibel. Then afterwards, it decreases by negative 10 decibel per decade from 0.1 radian per second until 5 radian per second. So this is the first break frequency is 0.1 radian per second. Second break frequency is 0.5 radian per second. Then it is back to flat at 0 decibel. And then after at 3 radian per second, goes down again at negative 20 decibel per decade. Then going down steeper at negative 40 decibel per decade. So looking from here, then we know that this transfer function should contain more poles compared to zeros, because the tendency is going down. So first, now the initial constant is at 20 decibel. So it should be logarithmic of 10. Different from 0 decibel. It's not 0 decibel. So then it means there is a constant K0. Initial constant K0. K0 equals to 20. K equals to K0 equals 10 to 20 decibel, and the K0 equals to 10. To 20 log 10 is 1. So 1 times 20 equals to 20 decibel. That's why this is the decibel of 10. 20 log 10 is 20, right? That's why the K0 equals to 10. Now B here is the first break frequency, or corner frequency at 0.1 radian per second. So we know that this is a simple pole at 0.1, because then afterwards it decreases by only minus 20 decibel per decade. So j omega divided by 10, j omega divided by 0.1 plus 1. Power minus 1. So this is a pole. That's why it is at the denominator. J omega divided by 0.1 plus 1. Then we have another corner frequency at how many? This one is 0.5 radian per second. This is also compensating the minus 20 decibel per decade from this simple pole. It becomes flat at 0 decibel. So this should be a 0 then. should be at 0, having the same slope, which is 20 decibel per decade, but only positive, yeah, polarity. And the pole is at 0.5. So it becomes j omega divided by 0.5 plus 1 as a 0, yeah. So as j omega divided by 0.5 plus 1. Then at D, it decreases again. The corner frequency is 3 radian per second. So this becomes should be a pole, yeah, because it makes the composite to decrease again by minus 20 decibel per decades. So we know that then j omega, the transfer function of this is j omega divided by 3 plus 1 power minus 1, because it is a pole. J omega divided by 3 plus 1 power minus 1. Then finally, we have another break at how many is that? 20 radian per second. Yeah, but now it decreases from further from minus 20 decibel per decade, it becomes minus 40 decibel per decade. So it adds minus 20 decibel per decade. So it should be another simple pole at how many? 20 radian per second. So it becomes j omega divided by 20 plus 1 inside parentheses power minus 1. Okay, then from here, then we can write the complete transfer function as h j omega equals to 10 plus 10 times j omega over divided by 0.5 plus 1 divided by this one. This multiplied by this multiplied by this. Okay. Yeah, that is the steps, yeah, to estimate the pole and zeros of the transfer function based on the Bode plot. Okay. If the slope is minus 40 decibel per decade, yeah, we assume a double real pole unless we are given more data. Okay, another example. Determine a transfer function from this composite magnitude asymptotes plot. Yeah, at 5 radian per second, it reaches 0 decibel. Before that, it has this slope of minus 20 decibel per decade. Then after that, it's flattened. Then at 20 radian per second, decrease again minus 20 decibel per decade. Then flatten at so this becomes 0 decibel. This becomes minus 90 decibel. Then after that, it decreases again at minus 20 decibel per decades. Determine the transfer function. First, this becomes the A, the pole at 0, pole at the origin. The pole at the origin crosses the 0 decibel at 0 decibel line at 5 radian per second. So j omega divided by 5, 5 divided by j omega. So this is pole because this is decreasing. So the magnitude of this equals at the origin, yeah, 5 log negative minus or 20 log this one, 5 j omega, 5 over j omega. Then at B here, we have a 0 because then after negative 20, it is compensated, become 0 gradient, 0 decibel per decade. So it means there should be a pole which increases by 20 decibel per decade at 5 radian per second. So the pole is j omega divided by 5 plus 1. At C, this is decrease again. So another pole. Hello? Yeah. The C here is another pole decreasing by minus 20 decibel per decades. Okay. And pole is at, the break frequency is at 20 radian per second. So this becomes j omega divided by 20 plus 1. Power minus 1. Then at 50 radian per second, it flatten again. So there should be a zero, yeah, that compensating the negative gradient by positive gradient 20 decibel per second. So this should be a zero at 50 radian per second. Then it decrease again at 100 radian per second by negative 10 decibel per decade. So this should be another pole, yeah, at 100. So the transfer function becomes dj omega. The first one here is this one, 5 over j omega. Okay. This is the k. This is the constant. The pole at the origin. Log, yeah, 5 negative 20 log j omega. So yeah, at negative 20 decibel per decade as a function of omega. And then at 5 radian per second crosses the 0 decibel line. At omega 5 becomes 0. Okay. Then this one, P0 at 5 is this one, 0 at 50 is this one, and pole at 20 is this one, pole at 100 is this one. Okay. 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 Any questions regarding the sinusoidal frequency analysis? Hello?
No question, sir.
Sir, I have question regarding the video.
Yeah. Martin, you are in market. Yes, Elisa, what is regarding the video?
So I am group 2, right? So I